Hey everyone, welcome to our fourth and final worked example where we're going to go through yet another full spectral assignment. Just to give a little PSA or a shout out ahead before you begin this video, it's a long video. This is a really long example problem. So I just want to say that I recommend you don't need to sit through this whole video all at once. In fact, I recommend that you don't do that. It's probably going to be best for you to take breaks in between each section of proton, carbon, HSQC, COSY, to sort of sit back, process the information, maybe come up with some guesses for yourself. When I sit down to tackle a problem like this from nothing, having never seen it before, I don't sit there and work until I've solved it. That is absolutely not how I approach these types of problems. I dive in, look at little bits of data here and there, get some ideas started, and then normally I'd take a break and go do something else. I wanted to include pretty much everything that you need to know about one example in one video, but turns out that takes a really long time. So I don't expect that you will approach the problem solving of working through these examples or your post lab in that same way. I expect that you should work on it over a course of days or weeks. That's why we gave you weeks to do it. To give you reminders about this, I'll put a little break kind of after each section so that you can remind yourself to get up, go walk around, do something else for a bit if you feel like it, or again, you're always welcome to work straight through. To make it easier to get back to this, if you do decide to take breaks in between, I'll give a link to the beginning of each section in the description, and they'll also be posted on the Moodle. The digital format of our NMR unit allows you to really work in the way that makes the most sense for you and your lab team, whatever your own pace may be, whether that's taking lots of breaks or taking no breaks at all. It's totally up to you. So with that, let's get into it. So just like the previous example, I plan to work through the 1D proton and carbon spectra and then look at our 2D data, then take all of those pieces and kind of put them together. We're going to see pretty much the same techniques and the same data in this example, but now we have a different and slightly more complex molecule. At least it's complex in different ways. So hopefully we're going to flex a few different types of NMR spectral muscles while working on this practice problem. I think this will be a really good one to get you set up to tackle your post-lab assignment. So let's begin with my favorite place to start, the proton NMR. And before we get going on analyzing any of these interesting peak shapes, we want to go ahead and give some names and labels to these peaks so that we know how we can refer to them later. Again, I'm going to use letters for the protons, and then we'll do some numbers for the carbon in a bit. So starting with A and moving down the alphabet, we'll get all the way from A to J. Now you may notice that I kind of skipped over what looks like a pretty important peak between H and I, but I'm skipping over it because this peak here is just water or some other contaminant. It's about in the right range for water, but the key here is that the person who put this together for us did not integrate the area under this peak, and therefore it means that it's nothing we need to be thinking about. It doesn't correspond to any of the protons on our molecule. So for those reasons, we are going to simply ignore it and pretend that it doesn't exist. Just like our chloroform peaks in previous examples, I'll just put an X through it. Now with the labels done, we can take a look at the integration and splitting. So I don't have to really write too much about the integrations because they're labeled out here for you pretty clearly. So when we see this 2.0 under A, that just tells us the integration is 2.0 and it stands for 2 hydrogens. Most of these are 2 or 1 hydrogens, rounding a little bit up or down as needed. The only one that may be a little bit weirder is 2.8. You'll have to round that a little further up to be 3 protons there. Based on these integrations, you may already have some ideas of which protons could belong where. I want to take account of some of these splitting patterns. When we first learn about peak splitting, we give you some really clean, clear-cut examples to give you an idea of where this splitting comes from and how it works. But in real life, when you're looking at real molecules, just like this one that's pictured at the top center of our screen, the splitting doesn't always work out as neat as we might hope. So because of that, we're going to see some, maybe not so nice looking splitting of these peaks today. I want to get some just initial impressions, first ideas written out on the page for what the splitting looks like. And then we can always come back to that later and make some edits if we need to, based on what neighbors are nearby particular hydrogens and what splitting patterns we would expect to see without looking at the data itself. So more on that later on in the video. Let's get some preliminary splitting patterns down. If we look at A, it looks pretty clearly to me like I can see 4 separate peaks there. So I'm going to label that as Q for a quartet. Moving on to B, It looks pretty much like a doublet to me, but I think there is some fine splitting happening here at the very tippy tops of those peaks. So that's definitely at least a doublet. But since I'm seeing what looks like a little bit of fine splitting, I'm going to put this down now as a doublet of doublets, and then we can come back and see whether we agree with that later. Similarly, for C, it looks kind of lumpy and kind of weird, but if we look closely, it appears to me that there's kind of a triplet looking piece there and a triplet looking piece there. So it's possible that this is a triplet with some complex splitting, or maybe a doublet with a little bit more complex splitting. With it being so weird and lumpy looking, let's just go with our gut, give it a simple assignment, and then we can come back and maybe expand on it later. So I'm just going to go ahead and call this a doublet for now, but I'm going to put a little asterisk by that to remind myself to come back and definitely check on it later. Looking at D, that pretty much looks like a triplet to me. We can always, again, adjust these as we go along. E also looks like a triplet, but I feel like I am seeing more fine splitting in those tops of those peaks. So we'll say triplet for now, but again, this one is definitely one we want to come back to. And what about F? Looking at F, it's very hard to tell. I'm definitely seeing more than a few splitting peaks happening here, and it's not really a pattern that I can make out very well just on inspection with my eyes without zooming in any further. So I'm going to start by calling this one a multiplet. When we figure out which proton F is, we can maybe come up with what the splitting should be, but for now, leave it as a multiplet. And then as we move along to G, it's not getting any easier. This one is definitely what I would characterize as super lumpy and weird looking. So again, I'm just going to call this one a multiplet. Not sure what's happening there. Same with H. There seem to be two kind of taller spikes sticking out of it, but there's a lot of complex things happening toward the base. So we'll call that one a multiplet as well. Same with I. Now J, finally, we have a return to something that looks like normalcy. It looks to me like a very fine, well-resolved triplet. No big deal there. Finally, we're kind of ending back in our comfort zone. So now that we have the labels, splitting patterns, at least preliminary splitting patterns, and integrations, we can move on to the carbon and see what is happening down there. Take a quick break here if you need one. In our carbon spectrum, we have a very similar looking situation to the previous example in that we have something that's way downfield down here, and then a bunch of other carbons that are at much lower chemical shifts. So looking at the structure, hopefully we can tell why that is. Again, we're in the 170 range. So that is just going to leap out to me and say that is our carbonyl carbon. Again, we're not really trying to nail down these assignments right away, but since it's just so far away and it looks a lot like the previous example, we're going to go ahead and pre-label that one as our carbonyl peak. We're also going to label it as carbon 1 because it is the furthest downfield. If we then look a little bit further, we see this sort of small stubby peak there. Again, that is going to be at 77. That is just chloroform. We can ignore it. And then we have a bunch more carbons here in the upfield range. Let's just go ahead and give those some numbers. And then do our sanity check to make sure that we are looking for 8 unique carbons based on our structure. So 1, 2, 3, 4, 5, 6, 7, 8. It checks out. Before we move on to the two-dimensional data, I do want to take a few moments to talk about some chemical shift ranges. Particularly in the proton NMR, we have a lot of complex splitting. We have a lot of single proton signals that are integrating for just one hydrogen. And it's a little weird because looking at our structure, we have a lot of CH2 groups. So it may feel a little bit strange and possibly intimidating that we have all of these single unique hydrogens that we have to parse out. Don't worry too much about picking out exactly which one is which at this moment. I want to help us slowly focus down to that level by starting to think initially about chemical shift ranges and where certain protons might be expected to show up. So we have proton A is way up here, much higher than everything else, almost at 4 ppm. And then we have a number of protons clustered here between 2 and 3 ppm. And then we have another set that are all clustered underneath 2 ppm. So thinking about these ranges and what they might be near will help us get some ideas about where to look on our structure when we start to try to make some assignments. So protons that are further downfield are going to be de-shielded, meaning that they have something electron withdrawing or very electronegative near them or next to them that is going to be pulling away some of their electron density. So it wouldn't hurt to start thinking about the things that are electronegative on our structure. First and foremost, one that is really screaming out to me is this ester oxygen. Of course, that's pretty electronegative, so that's going to be pulling in toward itself this way and this way. We also have the carbonyl to be thinking about. Normally, we think about that as really centering a lot of positive charge here at the carbonyl carbon, which is why we see the carbonyl carbon at the highest chemical shift in our carbon NMR. But it also means that the partial positive charge on this orange colored in carbon is also going to be withdrawing from the carbons next to it. So we could draw another small dipole moment that's pointing in toward that carbonyl away from our ring. So those are a few things to think about. The last one here is this nitrogen. Again, nitrogen isn't the most electronegative. It's less than oxygen, but it's still more electronegative than carbon. So we have to keep in mind that we're going to be pulling some dipoles in that direction as well. Then if we think about the places we haven't drawn in dipoles, we can assume that those are going to be much more similar to regular old aliphatic sp3 hybridized CH bonds that don't have a lot of other interesting functional groups around them. So with all of that, we just want to keep these three chemical shift ranges in mind, and then we'll come back to them when we have a little bit more data from our HSQC and our COSY. We can also think about chemical shift ranges for the carbon NMR, although with the exception of carbon number 1, it's not going to be nearly as dramatic as it is in this proton NMR. Clearly carbon 1 is outstanding in its field, way above everything else. And then we have a few carbons here that are a little higher and a few carbons here that are a little lower. But it may not necessarily be as clear a distinction or quite as cut and dried as it seems to be for the proton. That's where we'll make good use of our HSQC data. When we get a little more information from the COSY about the protons and start putting in some preliminary proton assignments, we can then use the HSQC to start thinking about which carbons go where and see if their chemical shift ranges make sense for their locations. Okay, I think we're ready to move on to the two-dimensional NMR data and take a look at that COSY. Take a quick break and maybe think up some assignments, then come back to it. All right, here's our COSY. There's kind of a lot of cross peaks going on here, so let's start as we always do by putting in our labels and putting in our identity diagonal to hopefully help minimize a little bit of the massive things that we have going on here. So always starting with our assignment labels on our protons just so that we can see what's what. And you should notice that this COSY example is plotted differently than the previous few examples that we've looked at, where before we had the low end of our axes at one side and then it was at the symmetric place on the graph on the opposite axis, but here it's actually plotted differently. So you just want to pay special attention to how you are labeling your peaks to make sure that you don't accidentally mislabel this peak as A, that one is actually J. All right, with our labels in, let's draw in the identity diagonal. And again, it doesn't exactly look like it goes quite across this box perfectly. So we'll just start down here, draw on a line, and try to line it up as good as we can with the center of these peaks. Let's start by getting rid of half of this COSY just because it helps me to focus a little bit. There are a lot of cross peaks in this one. It's a much more complex example than our last one. So I really want to try to minimize the intensity of this as much as possible by just straight up reminding ourselves that we can ignore everything that's in this lower half of our graph. And you are, of course, also welcome to ignore the top half of the graph, whichever one you prefer. So I'm going to take a moment to just put in all of these lines, and then we'll regroup to talk about which peaks are our cross peaks in a moment. So there's our vertical set of correlation lines. Most of them seem to run through cross peaks, particularly out here in the middle, but actually after putting in the lines at I and J, it doesn't seem like we run into any cross peaks here. We only hit the identity diagonal. So for simplicity's sake, I'm going to just go ahead and erase those annotations since they don't go through any cross peaks on the upper half of our graph. And now we'll go back in and do our horizontal lines to go over to the other axis. Okay, there we seem to have, again, a lot of lines. To me, it also looks like the last two lines I've drawn in at A and B don't actually hit any cross peaks on the upper half of the graph. So we're going to go ahead and get rid of those to simplify, even if just a little bit. So let's label these cross peaks. So following down this direction and over here, it seems we have a J to A correlation. Looking at this peak, sort of the next one, I'm kind of going from left to right here. That one seems to line up on the vertical axis with F and goes up to B. Going down along that line, it seems that this peak here could be a couple of different things. It looks like it might be B correlating to C, but it also definitely seems to go right through the center of D as well. So I'm going to call this peak D to B for certain, but that it also might be C to B question mark. We can come back to that and look at it more later to see if it makes sense. Moving on, up here we have a peak underneath C that correlates over to I, so I'm going to call that IC. Underneath that, it seems that H also corresponds with C. And then further down, E corresponds to C, and then just below that is the C identity diagonal peak there, which we don't need to label. Let's see if there's anything underneath D here. Looks like this peak falls underneath D and over to F, so that is an FD correlation peak, and then again we hit the identity axis there. Underneath E, looks like I correlates to E, and there's a small peak here that H also correlates to E. So since that's kind of smaller, more faint, it may be a longer range coupling. We'll have to see when we start filling in our assignments. Then nothing else except the identity diagonal. Underneath F, so it looks like F also corresponds to H, and there's a tiny little peak underneath here, maybe a little tough to see, but it is underneath there that corresponds to G and F. We're almost there. There's a lot of cross peaks, but we're nearly done. Moving on to G, it looks like H corresponds to G, and then we hit the identity diagonal. And last but not least, I corresponds to H there. Whew. Okay, take a break, blink your eyes a few times. This is a whole lot of things to look at. But given the number of lines and splotches on this page, it seems like it's actually a little bit less than I was initially anticipating coming into this. It does look like a lot of spots and a lot of signals, but again, we're only reading less than half of them. So now I'll take the liberty of deleting all of our correlation lines just so that this is a little bit easier to look at and read. Even then, it's still a little bit complex and clumpy. Okay, so we'll tabulate up all of those COSY cross peaks in a bit. Let's move on and analyze our last piece of data, the HSQC. Here is our HSQC data. Again, before we get into these correlation signals, let's go ahead and put our assignments back up on our 1D spectra. When we go to start labeling these carbons, make sure you're taking account of the chemical shift range. We're not going all the way up to 170, so this is not carbon 1 here, this is carbon 2. We're skipping 1 because that is a carbonyl carbon that is quaternary. It will have no hydrogens on it based on our knowledge of this structure. And then same as before, let's draw lines down and across to find our correlations. Okay, with our lines in, now we can label our hydrogen-carbon correlations. It looks like we have a peak down here where carbon 2 corresponds to protons A. Moving right along, it seems that carbon 3 correlates to proton B. But if you follow along that line, you'll also find this correlation corresponding to that same carbon. So this might seem a little weird because we don't see it all the time in our HSQC that we have multiple hydrogens correlating to the same carbon. When we stop to think about it though, that makes a lot of sense for particularly these protons B through F. We said that all of those signals B through F integrate to just one proton. And that means that some of these CH2 groups here must be split up into single protons in the one-dimensional proton spectrum. But we know they have to be bonded to the same carbon. It would make sense that multiple hydrogens could be correlated to the same carbon. So I think that is exactly the case of what's happening down here, where 3 also correlates to D. Moving right along, we have 4 here that seems to correlate up to C, and we see a similar thing here that 4 also correlates to E. So those are probably going to be pairs of methylenes that have, for whatever reason, slightly different chemical shifts in the proton. 5 seems to correspond to F, 6 to G, and then we have a little bit of a weird situation happening here as well. It kind of looks like that big splotch underneath H kind of touches carbon 7's line and kind of touches carbon 6's line. So that's kind of weird. Could a single hydrogen signal correspond to two different carbons? Well, yeah, it can. The thing that we don't have written down here on our spectra is that the H signal was for two hydrogens, so they don't necessarily have to be on the same carbon. One of them could be on carbon 6 and one could be on carbon 7. So let's read it like that for now, and if it turns out that this is just a blotchy H signal and that's not really what's happening, we'll be able to sort it out later on. So let's say that this is a 6H and a 7H correlation peak. 7 also seems to kind of correspond to I. Again, the line isn't perfect there, so I'm not certain about that. Let's put a little asterisk to remember to come back to that it doesn't seem as nice as we might want it to be. It looks like 8 corresponds with J. Okay, so again, removing these lines now that we're done using them, and we can just tabulate up this data later on. Feel free to take a break, think this over, and come back to it. All right, so with that, we've put some correlation labels on all of our 2D NMR data. We have kind of parsed through as much as we can. Now it's time to start thinking about where things might go on our structure. For that, I want to return to the one-dimensional NMR so that we can start to think a little bit more about our chemical shift regions and put some preliminary guesses in place. I want to start like we did with the last example by going back to the proton data and then using the splitting and the integrations, we can start to put some preliminary guesses in for protons. For this example, it may be a little bit more important to think about chemical shift range because we have a few more signals that are in kind of a tighter range than in our previous example. So we have a little bit more detective work to do here. We'll have to think a little more carefully and critically about chemical shift. So before we get to the really nitty-gritty details of chemical shift, I do want to look at the outliers. This is what we like to call taking advantage of some low-hanging fruit first to kind of warm us up to deal with the more challenging, less obvious peaks. So looking at the kind of extremes of our one-dimensional proton spectra, we have signal A quite near the top downfield with an integration of 2 protons. And then we also have J that's the lowest. I think we agreed that we were going to call this basically 3 protons. It's not exact, but it seems to make sense that it could be 3 given our structure. So I want to look at those 2 outliers, partly because they have more of an interesting integration than all of our 1 hydrogen peaks. They also have, to me, the most clear splitting of all of the peaks represented here. So we looked at A and we said that looks like a quartet, and we looked at J and said that looks very much like a triplet. So thinking about our neighbors and splitting, A, to be a quartet, would have to have 4 minus 1, 3 neighbors. And the only place on our molecule that has 3 neighbors is right here on the ethyl group of our ethyl ester. And I think that makes sense based on our chemical shift analysis as well, because in this region up here that I highlighted earlier, that is the furthest downfield, meaning that we must be adjacent to something pretty strongly electron withdrawing, at least the strongest out of all of the other functional groups in our molecule. And to me, that singly bonded oxygen is going to pull with a pretty strong dipole, so I think this makes sense both by splitting and by chemical shift. So let's go ahead and label that in. I'm just going to draw 1, but that's okay. 1 HA there, but there are 2. And that will come in handy when we go down to J, thinking about J as a triplet. If we think splitting there, we have 3 minus 1 neighbors should be 2 neighbors, and those neighbors are most likely HA. And you say, well, yeah, I mean, sure, Grace, but you also have CH2s at all these other positions. Why are we ruling those out? We're ruling those out because of our integration here for 3 protons. We know that methyl group is the only place that has 3 equivalent protons, So it has to be this position here, HJ. Okay, with that low-hanging fruit taken care of, now we can dive in a little bit more carefully to these other two regions of interest. So we have the chemical shift region kind of here between 3 and 2, and then everything else that is lower than 2. So you're welcome to go back to your proton NMR chemical shift table. That will definitely be a useful resource to you here. But before you go and dig that out from your notes from last semester, we can also just think about this in a more kind of loose way. Like I said, talking about things that are nearby, functional groups that are adjacent, that will exert some kind of shielding or de-shielding pull on these protons. So with that in mind, I want to start with the next most downfield shifted protons, B and C. So B and C are not as high as proton A, meaning that they're not adjacent to something like that sp3 hybridized oxygen, but they're also not super low either, meaning that they must be next to something that's fairly withdrawing. So the remaining positions that we have that are sort of adjacent to withdrawing groups, I'll highlight again with some dipoles. We have the nitrogen of this cyclic amine that's pulling in toward itself. And then you also have the partially positively charged carbon of our carbonyl pulling in that way. So these orange highlighted positions here are probably going to be next in line for most withdrawn by their adjacent functional groups. So if we think about the total number of protons that we have there, we have a CH2 at this position, a CH2 at this position. This is just a CH. That is a total of 5 protons. And I think you'll see that conveniently, we have exactly that number of protons in this region here. So now it's just a matter of deciding which ones go where. If I were you working on this problem, I would just go ahead and take this pretty literally just at face value to say, I'm going to take the positions that are next to the most withdrawing functional groups and then just fill those protons in order. And then we'll take a look at them afterward with a little bit of splitting analysis to see if the number of neighbors based on their perceived splitting makes sense with the assignments that we've put in place. So let's get rid of these orange annotations here and start filling in some proton identities. So choosing between the two positions, the ones that are next to the amine or next to the carbonyl, I'm going to just go with the electronegativity of those atoms. So we're comparing nitrogen to carbon. Even if it is a partially positively charged carbon, nitrogen is still going to be more withdrawing. So I would imagine that these two positions will be the second most highest withdrawn positions after position A. So I'm not really certain whether we have B and C on the same carbon or some other mixture. That's how I would just read it to start. I would guess that B and C are probably together here. And I'm going to guess that they're on that side of the ring because, again, they're a little closer to the carbonyl. The inductive effects of that carbonyl are going to be diminished as we go away from it. So B and C aren't feeling a lot of inductive withdrawal from that carbonyl, but they would certainly be feeling it more than the opposite side of the ring, which is much farther away from the carbonyl. So because of that, I'll put H, D, and E on the far side of our ring there. And that leaves us the last remaining proton, F, to go at this position here, alpha to our carbonyl. Just doing a quick sanity check about the chemical shift of proton F. In our second example, we also had an ester compound, and we talked about the appearance of those alpha protons next to a carbonyl at just about 2 ppm. That makes really good sense for the signal at F because it's just above 2 ppm. That checks out for the shift of an alpha carbon's hydrogen. Okay, I think we've got some good starter assignments there. Let's try to fill in the blanks with G, H, and I. So the only remaining positions on our molecule are up here. And then if we think about the number of protons that we have left to assign, we have a signal for 1, a signal for 2, and a signal for 1. So we have 4 protons left. That's good. We have exactly the right number of protons that we should have based on the structure and the integrations that we were given. So we can just fill these in at these positions. It may be a little bit challenging to decide which ones go where, but again, these are just preliminary. So let's come up with a guess and then see if we can prove or disprove it later on. Keeping in the theme of considering chemical shift, we have one proton at G that is slightly higher in chemical shift than the other ones. Again, they're all relatively low, but because that G proton is a bit higher, I would assume that that is the one that is next closest to our carbonyl carbon. So I'm going to put Hg at the position closest to our carbonyl. And then we have H and I remaining. We said that H is 2 protons, and looking at our HSQC data, we saw that it seemed to correspond to 2 different carbons. So I think it makes perfect sense to split up 2 different protons H here, because that's what our HSQC data is telling us that we need to do. We'll come back and double check with that later on. But I'm going to fill in HH, also attached to the same carbon with Hg, and then the other HH, we'll call it H prime, will go on the adjacent carbon here, along with HI. Ooh, okay, we did it. We've got a lot of labels on there, and it doesn't look particularly good to me right now, but that's why we're going to ask you to put your final labels in on ChemDraw so that it will be nice and neat and not look like kind of a messy forest of different hydrogens with different labels like I have here. So now to start sorting through this messy forest of hydrogen labels that I have here, I next want to look at the COSY information to see if everything we've assigned so far relatively makes sense, and look for some cross peaks that will tell us, oh yeah, the position for hydrogen F makes sense because we see these splitting peaks. And that hopefully will tell us if we've gone astray anywhere and help confirm the things that we feel pretty good about. Another way to approach this would be to start thinking more deeply about the type of splitting you're seeing here in your one-dimensional NMR. That's kind of the approach we took with the last example to help us get started on finding some positions. Because of the nature of the structure and the complexities of the splitting of some of these one-dimensional protons, I'm going to save that for a separate video that you can watch if you so desire. Thinking about the splitting in this careful manner might be really helpful for your post-lab, so you may want to check that video out as well. For the sake of keeping this example as short as possible, we'll go straight to the two-dimensional data to start ruling things in and out. Before we move into using the 2D for our analysis, maybe take a break. So based on the assignments we've given so far and some of the splitting of these peaks, I think we want to highlight a couple of specific protons to look for their correlations in the COSY, specifically proton F to start. Based on where we put it in the structure, it has a lot of neighbors, right? In the COSY, we would expect to find a correlation from F to H, from F to G, from F to B, and F to C. If we see all of those, then yeah, we're probably in a pretty good position with all of these signals there. If we don't see some of those, then maybe we have some adjustments to make. The other proton we might want to look at would be maybe HB or HC. I'm going to say HC to start because we left this sort of asterisk here with our assignment for the splitting on peak C. It looks like maybe it's more complex than a doublet. And based on the place that we put it in our molecule, it should really look kind of a lot like B. It doesn't look as much like B as I'm expecting. Again, go see that other video to think more deeply about the fine detail splitting we would expect to see in the 1D NMR. So those are just 2 to start with. You can start anywhere. All right, so we'll target HF and HC in our COSY. So let's head down to the COSY. So again, since there are a lot of cross peaks, I'm only going to pick out the ones that relate to F and C to start with, and then we can come back and look at more later. So just scanning across here, IG, I'm looking at this FH here, GF, FD, and FB looks like. I don't see any others, so let's go ahead and tabulate those up. And here I'm labeling them as kind of coordinate pairs. You may notice that I inverted the coordinate pair there. It doesn't matter because right coupling is a two-way street, so it's F to G or G to F, doesn't matter. And then for C, let's look at what we got here. We've got IC, HC, EC, and we said maybe a C to B here, but that was kind of a question mark. So let's write all of those down and then take them up to our 1D spectra and look at them. Starting with proton F, let's look and see if all of those correlations add up. We were looking for an F to H correlation, that checks out. We were looking for an F to G correlation, that checks out. We were looking for an F to B correlation, and we were looking for F to C, but we don't have that. We have F to D instead. Okay, so that might be a little bit of a problem. We'll just draw a little asterisk next to that, come back to it. Since we're missing that correlation for F to C, possible that C doesn't go there. Let's use the C correlation peaks to see if that makes any sense. So if C is supposed to be where it is, we would expect to see that CF, which we're not seeing. We would expect to see this B to C, which we said maybe we see that here, but we're not 100% certain about that. But I think that proton C is definitely too far away from I. We don't see that, and it's really far away. We wouldn't expect to see it. It's also pretty far away from H. We wouldn't expect to see coupling there. And it's pretty far away from E as well. Proton E is here. Somehow its little bond got erased. But normally we wouldn't see this kind of coupling across a heteroatom like that. The heteroatoms can sometimes disrupt the coupling. So we wouldn't necessarily expect to see that one. Even if we did, we're still only at 50% of these cross peaks making sense. So I think C is probably not in the right spot. We are going to have to figure out a way to put that somewhere else that makes a little bit more sense. So I'm going to erase these purple highlights here and put a big red highlight around proton C that we need to move that somewhere else. We want to move it to a place where we would be in close proximity to I, H, and E. So if we look at where those are, here's I, here's H, here's another H, and here's E. It seems like we actually want to be kind of on the other half of the molecule over here and not over there. So maybe we could switch with D. That's the only one that's kind of not circled over here. So that seems like a good spot to me. Before we make that switch, let's go back to our COSY data and look for some of the correlations that D has and see what D should be correlating to see if maybe we could just do a little swap there. Back to our COSY data here, let's tabulate up everything that we see for D. So I don't see anything near the top, but I do see FD and DB there. I think that's it. So DB and DF. Just bring those up to the top here and kind of add them to our list of COSY information here. So looking for these correlations, we want to see D to B and D to F. So B and F are both over here, again, sort of on the wrong side of the ring from where we put D. So it seems that D is in the wrong position and C is in the wrong position. We might be able to swap them, but I think we can use our other piece of data to help us figure it out a little bit more clearly, and that is our HSQC. So let's pop down to the HSQC and think about the carbon-hydrogen correlations. In fact, this was maybe the fastest way to do it would be to look here first. I wanted to take that chemical shift approach of getting some assignments in and then coming back to them later. If you prefer to work in that way, where you're looking mostly at the protons and then at the COSY and then at the carbon, that's fine. If you want to be looking back and forth between all the pieces of data all the time, that's good too. So looking at our HSQC, when we did these assignments initially, we drew our lines across and we said, oh yeah, it's a little bit weird, but it looks like B and D correlate to the same carbon and C and E correlate to the same carbon. This means that B and D are bonded to the same carbon and C and E are bonded to the same carbon. So if we look back at our structure up top, we have D and E together and B and C together, whereas that's not what the HSQC tells us. The HSQC showed us a correlation between B and D on the same carbon and C and E on the same carbon. So it looks like we do want to switch D and C, and then hopefully our COSY peaks will make a little bit more sense. So let's get rid of these annotations and change them out. C and E together, B and D together. Okay, with that, let's revisit the COSY information and see if it works any better. So F to H, F to G, and F to B didn't change. F to D, though, now is here. That checks out. So that seems better. Now let's look at proton C. We had a C to I, a C to H, and a C to E correlation. So C to E now is in place. That's a geminal coupling. C to I is now in place. That's a neighboring or vicinal coupling. And C to H, it's H prime, but we can't really tell the difference between H and H prime on our 1D or 2D spectra. So I think CI, CH, and CE all check out. That seems good. Since we've got the data for D here, let's check D as well. D correlates to B, there's our geminal coupling, and D correlates to F. Perfect. So it looks like proton F, B and D, and C are all in the right place. I think E is probably pretty good too, but that's maybe one we should look at next just to make sure that everything else makes sense. So I think that's a really good start. What I'll do next is just tabulate all of our other COSY peaks so that we can go through in the same way and look for these correlations. All right, so skipped over tabulating all of that information and bringing it up because I'm confident y'all can do that on your own. So I tabulated up what I think are all of the remaining cross peaks that we haven't talked about yet. Yeah, I might have missed some, but you can always go back and check your work multiple times to make sure that everything adds up and makes sense. And doing things like putting little check marks next to your peaks once you are confident that they make sense, just to help you make sure you caught everything. So let's just run through the rest of these. Some of them might be redundant to one another, just because I was going by letter. So I picked out all of the J couplings, all of the E couplings, all the H couplings, and all the I couplings. So let's go through one by one just to make sure they make sense. So the first one I feel like is a freebie and a gimme. J corresponds to A. We knew that over here from our splitting of that nice ethyl group. It's a splitting that we feel pretty comfortable with. So I'm comfortable to call that done. Let's move on to E. We said that one we weren't sure about of these ones that are sort of close to the nitrogen. So let's check our correlations there. So we knew already that C correlates to E. That's our geminal coupling. We feel pretty good about that. Check. E also correlates to H. In this case, it's H prime, but that's okay. And E correlates to I. I think those all check out. Moving along, we have H. So H is a little bit weird, right? Because it is these two different protons that just happen to come out at essentially the same chemical ship. But that's why there are so many different correlations for peak H, because it actually counts as two different protons. So H to C, we have an H prime to C, that's good. H to E, we just looked at that as well. H to F, now it's probably not H prime here, it's this other H to F there, seems good. H to G, this is a little bit weird. This could be two different things. This could be H prime to G as a vicinal coupling. It could also be H to G as a geminal coupling. Either way, we have both. And then H to I, again, same thing there. That could either be a geminal coupling of H prime to I or a vicinal coupling of H to I. Whew. Okay, that's a big old mess of highlight peaks. Let's get rid of a few of those. So that's one of the things that's a little bit weird about this particular example is just those H protons being right on top of each other makes it a little weird and gives a lot of these different cross peaks. But I think all in all, what we've got so far makes really good sense. All right, last but not least, let's talk about I. So we are expecting to see an I to C vicinal coupling, seems good. I to E similarly, and then I to H. Again, this could be either a geminal coupling or a vicinal coupling. Great. So some of that was pretty redundant, but it's always good to go through just to make sure all of the peaks that you're visualizing make good sense. So with all of that taken care of, I feel pretty good about where these protons are. Let's do the last little bit and start filling in some carbon assignments. So last but not least, we'll just take all of this HSQC data. I'm going to make a list on the side here, tabulate it up, and then take it up to the top so we can start labeling some numbers on our structure. All right, there's our HSQC data. So now we can start to fill in some carbon numbers. Let's use red. And I think I'll label the carbons on this lower structure down here, just because there is a lot going on that top structure already. So 2 we said was A, that's at that position, and we know 8 was the J protons that are next to it. Then going again in numerical order, 3 was here with B and D, 4 was on the opposite side with C and E, 5 was at the same position as hydrogen F, 6 was G and H, which we decided were the top two up here. And then last but not least, H prime and I down there at carbon 7. And of course, carbon 1 is our carbonyl carbon. I nearly forgot about it because it doesn't show up in our HSQC data. Okay, so hey, we're pretty much there. The last thing to do if this were your post-lab assignment would be to get all of your assignments on the same structure and fill out the data table. We don't have a data table for this one, but you could practice filling one out if you like. The one last thing I do want to leave you with is for this example and one part of your post lab, you have a lot of these grouped CH2s, right? And in my video where I talk about the splitting of these in more detail, I talk a little bit about the different positions in, say, a chair structure. So thinking about axial, equatorial, and that kind of thing. We wouldn't try to ask you to distinguish which proton is axial or equatorial or up or down for this type of post lab assignment or practice example, because maybe we could do it, but it's just way more than we need to do. Especially for this example, we don't know anything about the stereochemistry here. So while we could maybe make some assumptions and parse through with what we know about the splitting, we're not going to ask you to go to that depth with your analysis. So it's totally fine for you to say hydrogens B and D are on the same carbon, and that happens to be carbon 3, and they're at this ppm and they exhibit this type of splitting. The last piece of detail that we would be looking for your post lab is to give us Hertz values for the coupling. Since we don't have a Hertz axis here, we just have a chemical shift axis, it's going to be too hard to measure what the small couplings are there. But for your post lab example, we've given you plenty of good zoomed in regions and Hertz scales so that you can fill in all of that data. All right, we made it through this one. If you have any questions, you can leave them in the comments or stop by my office hours. Thanks for watching.